Okay, everybody, section 4.3 is a strange one in that there's really two concepts that the authors decided to cover within this section, and for my money, they really don't have a whole lot to do with one another. So the first thing we're going to talk about is the mean value theorem, and if I think about it, everybody, I'm going to knock out really just maybe these first two slides here, and then end this video and then start another one that deals with the transition into some of those things that we are going to be doing later on within this section and within this chapter. Because once we get into behavior of a graph here pretty soon, and then we talk about where a function is increasing or decreasing or what we call monotonic, this really relates much more to what we're going to be doing in sections 4.4 and 4.6. So I think this is going to be a pretty short video while we just talk about the mean value theorem. Now, the mean value theorem is the second, and we will abbreviate that oh so originally as MVT. It's the second of the three big theorems that we talk about in first semester calculus, everybody. The first one we discussed was the extreme value theorem back in section 4.2. That just guaranteed that a function that was continuous on a closed interval had an absolute max and an absolute min. Actually, I take this back. I've got my order wrong. The first one we talked about was the IVT, the intermediate value theorem, which we did back at the end of chapter 2, if I'm not mistaken. And that was the one that said that a continuous function can't skip values. Anyway, get on the topic, Mr. Fontana. The mean value theorem is actually probably one of the simpler ones of those. So here's what the mean value theorem says. Every good theorem should be written in if-then form. And the if, everybody, the hypothesis, is what has to happen for this function to apply. So the mean value theorem only applies to a function, f of x, that's differentiable on an open interval from a to b. The derivative has to exist everywhere in between. And if it does, then the conclusion tells us that there exists at least one value c, sorry for the spacing there, everybody, there's one value c in this open interval here from a to b, such that, and here's the big takeaway, guys, so we need to make sure that we get this written down correctly, f prime of c is equal to f of b minus f of a all over b minus a. Now, that probably doesn't set your world on fire right there, everybody, and it probably doesn't make it look like, oh my gosh, we just learned something amazing right there, but let's try to, that was supposed to be hollow. All right, let's try that again. That was supposed to, let's not do a fill there. All right, so let's now talk about what the mean value theorem says and what it's actually useful for. Well, before we go any further with this, I was really hoping that you guys could tell me, or that you would recognize on your own, what the two sides of this equation indicate. We've got f prime of c over here on the left, and far more complicated, f of b minus f of a over b minus a on the right. Well, what I'm hoping you guys know is that with f prime of c, we're talking about the derivative of this function evaluated at a specific x value called c. What that is, everybody, is the slope of your tangent line to this particular curve, y equals f of x, at the spot where x equals c. What you have over here on the right is a difference quotient, and what we're really finding here, everybody, is the slope between two ordered pairs. That, then, is the formula for the slope of a secant. So what the mean value theorem says is that the slope of a tangent line to a curve has to equal the slope of its secant line as long as the function is differentiable on this interval here from a to b where the secant line is defined. Then there's got to be at least one, although there could be more, values of c where the slope of the tangent would equal the slope of the secant. So, probably a good idea just to take a moment now and try to illustrate what it is that we're talking about here. Now, it really makes no difference at all where, come on now, where your axes are and whether this curve is positive or negative or who cares. But let's just go ahead and let's draw some random curve. And if we go back to the hypothesis, the if, all that matters is that this function is differentiable on an interval from a to b. So what does differentiable mean? Smooth, continuous. It can't have any corners, any cusps, it can't have any jumps or holes or asymptotes. So basically, don't think too hard and draw something nice and easy. So it can be interesting, guys. It could be a curve that does something like that, almost like a trig wave, and then we'll make that one shoot down here. And what we want to do is we want to define this curve here on an interval going from A to B. And I've probably made this more complicated than I needed to, but that's okay. I'm going to go ahead and say that my A value is going to be located right here, and that my B value a little bit further down is going to be located right here. Now, what's going on? At A, there's a Y value right here called f of A. And at B, if I shoot up straight here, there's a Y. That's not supposed to happen. There's a Y value right there that would be called f of B. And in that interval, everybody, we can, of course, create the one and only secant line defined, nope, that's not it, the one and only secant line defined by those 2 points, and it maybe looks something like that. All right, so that's your secant line, and of course it has a slope to it. And you might even want to write here that the slope of that secant is equal to, as we've been saying for a few months now, f of B minus f of A all over B minus A. Now, what the mean value theorem tells us is that if that function is differentiable on the interval from A to B, and the graph that we drew does exactly that, then there's got to be at least one value C in this interval here in between A and B, such that the slope of your tangent line, f prime of C, has to equal the slope of your secant line that we just came up with. So they're telling us now that there is at least one point in between A and B where the slope of the tangent would equal the slope of the secant. And I am just going to eyeball this right now, guys, but I think one such value is maybe right here. If I called that C and went down to the curve itself here and now tried to draw the tangent line to that curve passing through that particular point, well, it's certainly not perfect. But I'm hoping you guys would look at this and say, yeah, it's at least conceivable, maybe I can move that up a little bit, it's at least conceivable that there's a tangent line right there, oh, I had it, a tangent line right there through that point that's parallel to the original green line. That, though, I think, is only one such value. I feel like there's another one maybe right about here, just shy of that peak. And if I called that C2, maybe there's another tangent right there that also looks like it's parallel to that green secant. And as luck would have it, I think there's maybe a third one right here at a value that I'll call C3. Please no C3PO jokes, everybody. That would just be too easy. So it kind of looks, everybody, like we've come up with a curve right here that's got 1, 2, 3 tangent lines now that are parallel to that secant line. And sure enough, where do all 3 of those x values occur? C1, C2, C3. They're all greater than A and less than B. So they're all elements of that set, of that interval there in between A and B. Now, this is a more complicated version of what you'll normally see. Usually, it would be a much simpler curve, so you don't need to draw this down, guys. But even if we just had something like a simple parabola that looked something like this, okay? And if we just picked any 2 points on this curve, like maybe this one right here and this one right here, as long as the curve is continuous and differentiable, meaning that there's a smooth spot, then there is probably at least one point on this curve here, everybody, where the tangent line, and I'm thinking it would maybe be right here on this one, where the tangent line would have to be parallel to the secant that you just drew. And again, I didn't do a very good job there, but I'm hoping you guys can see that at least in theory, that should, there you go, that's better, that should probably happen. And the mean value theorem tells us that will happen any single time we have a function that's differentiable on that interval from A to B. So it's not a real complicated theorem. You guys are going to need to know this formula right here, so put a star by that. All right, and let's see what it looks like. The other good thing is, very often, when they ask you to do a problem that uses the mean value theorem, they are very explicit in their directions, and they'll say something like, use the mean value theorem to figure this out. So let's see what's going on in this problem right here. Find a point C. Really, it should probably say find all. Oh, that's not what I wanted. Cancel that. It probably should say find all points C, because it could be more than one, that satisfy the conclusion of the mean value theorem for this function on this interval. Okay, so what do we need to know, guys? The formula for the mean value theorem is f prime. Dang it. Let's do that again. All right, you go away. Here we go. All right, let's try it again, Mr. Fontana. That f prime of C is going to equal a difference quotient now of f of B minus f of A all over B minus A. So this left side, f prime of C, means that we have to take the derivative of this function and evaluate it at an x value of C. So the derivative of that, pretty easy to do in your head. That's just going to be a 6x, but we're going to put a c in there and make that a 6c instead. Now, I'll tell you right now, probably 90% of the people that do this problem or this type of problem forget to replace the x with a c, and they end up just putting a 6x there. Then they're solving for x instead of c, and you know what? That's fine. We're not going to panic too much about that. Now, the right side is where we find the slope of the secant, and this is just a little bit tougher. Up in the numerator, there's two values we've got to find that we don't know yet. F of B, and our B value here is 4, and then F of A, where our A value is 1. So you might want to do this off to the side and just try to knock this out before you go too much further. F of 4, the 4 squared is 16, times 3 is 48, plus 2 is 50. Trust me, kids, I am a professional. Put the 1 in there for F of 1. 1 squared is 1, times 3 is 3, plus 2 is 5. So up in the numerator, f of b, the ending y value, is going to be 50. Minus f of a, the starting y value, is going to be 5. All over b minus a is going to be a 4 minus 1. Just a real quick reminder, you might have I don't even want to say misinterpreted. You might have interpreted this differently, that this was the ending point and this was the starting point. And that's fine if you do your numerator in the opposite order that I did. As long as you do the same thing down in the denominator, that'll work out just as well. But regardless, we're going to try to keep this simple here, and let's go with that. Okay, so back to purple here. There is nothing to do with 6c right now, guys. That just is what it is. But this expression here, the 50 minus 5 is going to be a 45. The 4 minus 1 is a 3. And last I checked, 45 divided by 3 is 15. And now we're going to divide both sides by 6, which maybe doesn't work out quite as nicely as we would like, but it could be worse. Let's divide a 3 out there. We're going to get c is equal to 5 halves. Going back to the directions, find all points C that satisfy, there you go, the conclusion of the mean value theorem. Well, we only came up with one. There's a reason that makes sense, and we'll get to that in a second, everybody. We only found one, and the quick question what you should have here is this C value right here contained within that interval from A to B? And sure enough, 5 over 2 is 2.5. That is in between 1 and 4. So this, everybody, is our answer to that problem. Now, the thing I wanted to come back and talk about was, why does it make sense that there's only one solution? So let's pay attention to the fact that in this particular case, this certainly will not always be the case, but in this particular case, your function, f of x, is a second-degree polynomial. Now, you guys know enough about the power rule to deduce then that your derivative, f prime of c, will be a first-degree polynomial. What's happening over here on the right? That's always going to be a constant, like 15 over 6. So what we ended up here with was a first-degree expression equal to a constant. That's what you call a first-degree polynomial equation. And the number of solutions to a polynomial equation can never be more than the degree of that polynomial equation. So a second-degree function gave us a first-degree derivative, and a first-degree derivative equal to a constant can only give us a maximum of one solution. And that is why I was not surprised right here when we came up with only one value. Now, if I go back to this example that I just made up, that's a mess. All right, let's take a look. And assuming that this was a polynomial function, let's see, guys, we have different end behaviors. It goes down on the left and it goes up on the right. That means that this would have to be an odd degree function. And I see 1, 2, 3, 4 turning points. That means, everybody, that f of x, your original function, is a fifth degree function. So I'll just call it ax to the fifth plus yada yada, who cares? And that means that its derivative, no, Mr. Fontana, that means that its first derivative, f prime of x, would have to be, well, really, it'd be 5a times x to the fourth plus blah, blah, blah. That means that the first derivative would have to be a fourth degree polynomial. And when you set that fourth degree derivative equal to your constant value, that would tell you that in this case, you should see a maximum of 4 solutions. It looks like here we only came up with 3, C3, C2, C1. Truth be told, there probably is another one right over here. That kind of looks parallel to it as well, but that value is outside of the interval from A to B, so we get to just ignore that. Okay, guys, that's really the long and short of the mean value theorem. Okay, we could do more, but honestly, I think you probably get it. So that's the one equation that you guys need to know, and that's how to apply it. So at this point, I am pretty darn sure, I think I deleted the homework assignment off of these notes. I'm pretty darn sure that the only problems that I assigned for you guys out of the 4.3 homework dealt with the mean value theorem. So I'm going to stop this video right now, can't believe I remembered to do that, and say that at this point you're probably good to try the homework from 4.3. Then I'm going to come back in just a minute, do the rest of these notes as a separate video, and really those notes should probably be thought of or looked at when you're working on your homework on 4.4 and 4.5. So, mean value theorem, hopefully not too bad for you guys. Let's give that homework a try from 4.3, and you guys let me know if you have any questions.